All right, welcome. My name is Matthew. We're going to be solving these three problems from homework 1A. This is fluid mechanics. So we'll start with this first question. Derive the basic equation of statics. dp dz equals negative rho g. So to solve this equation, or at least get to it first, we have to start by thinking where this equation really comes from. And the easiest way to do this is to draw out a picture. And we're going to imagine a fluid in a container. And we want to try and find how the pressure and the density and the depth of this water, everything is related. So the best way to do this is to take a small amount of this fluid somewhere inside the container, and we're going to imagine this as a differential unit of volume. So if I blow this up, we can picture this as a differential unit of volume. We'll pick a cube, it's the easiest shape, and we're going to give this differential unit dimensions dx, dy, and dz. Obviously this assumes a few sign conventions, so for the sake of this example, upwards is going to be the positive z direction. Okay, and that's going to make our math a little bit easier later on down the road. All right, so the best way to approach this then is think about what kind of forces are on this little differential unit of volume. So let's go ahead and write those out. So there's a few different forces, as we can imagine, on this differential unit of volume. The first and most obvious one is gravity. If we can remember from Newton's laws, we know that the force of gravity is equal to the mass of this differential unit times acceleration, which in this case is gravity. Since we said this is the positive z direction, we have to make the note here that gravity is equal to 9.8 meters per second, and gravity acts downward in our scenario here, so that's why it's negative. Okay. So this is the force of gravity on a differential unit of volume here. Next we have the force due to pressures on this, and there's pressures in all directions, but in this problem we're concerned with the z direction. So we're going to be focusing on the pressures upwards on the bottom of this differential unit and downwards on the top of the differential unit. We can kind of write this out here as force on top, force on the bottom, and they're going to be different just based on the presupposition that we know that force due to pressure changes with volume in a fluid. We're going to prove that here shortly, but for the context of this example, that's why. So they're at different depths here, and the difference in their depths really is the difference in the differential unit dz. So let's call this force down here the force at z, depth z, and then we'll call the force up here the force at depth z plus dz. And that's going to make an important distinction later on down the road. So we have these forces acting up and down in relation to the plane, this plane here on the top and bottom of our differential volume. So what is this force equal to? We have the force on the top and the force on the bottom. And how are these forces related to pressure? Well, we know through our relationship from pressure equals force over area, right? That's our units like pounds per square inch or KSI or something like that. We know that these forces are related to pressure and area through this relationship. Okay, so we have the pressure on the bottom and the top, and what area are they over? Well, it's the differential unit area dx times dy. So dA, dx, dy, and then we'll need this later, but obviously the volume of this differential unit is dV equals dx dy dz, okay? So let's rewrite this expression for both the top and the bottom forces here. So we have the force at the top, that's z plus dz. This is equal to the pressure at the top of our differential unit, z plus dz, times the differential unit area, dx times dy. So we'll just write that as dA. Okay, and then we also have the force coming from the bottom of the cube. It's Fz equals pressure z times, again, the differential unit area. Okay, so one important thing to know about this differential unit volume in our fluid is that it's not moving. And if it were, it's moving at a constant velocity, which means it's not accelerating. Okay, so what we can draw from that is that the net force on that differential unit volume is 0. All right, so if we add up all these forces that we just drew out, they should equal 0, and that's going to be the basis for deriving this equation here. So we start with our first one here, gravity, okay? So we have the mass times negative gravity. Now, what is the mass of this differential unit? Well, this is where the relationship between mass, volume, and density come into play. We know from our physics courses that density, illustrated by the variable rho here, is equal to mass over volume, okay? And so if we illustrate mass here as density times volume, in the context of this scenario, mass is equal to density times the differential unit volume, dV, which we expressed earlier as dx dy dz, dV for short. Okay, and to that, we need to add these two forces. So we have, let's see, this force is in the downward direction, so that one's going to be negative. So I guess we can start with this one, upward positive. Pressure z dA minus pressure z plus dz dA. All right, and this all equals 0. So we can rearrange some of these things to make this a little easier on ourselves. We're going to get pressure on one side of the equation and the rest of our variables on the other. So let's keep this over here. We're going to simplify this, rho g dV, okay? And on this side of the equation, we can get, let's see, we'll get pz plus dz minus pz, and I'm going to go ahead and factor out dA right now. Okay, that just makes it a little easier for us. And recall that dV is the differential unit volume of our cube here, and that's equal to dx dy dz. Now, we can split this up, make this a little easier on ourselves, and call this dA, which is dx dy, times dz. Okay, so we still have dV there, it's just broken up. What that's going to allow us to do is cancel out the differential unit area on both sides, which makes sense because they're the same on the top and the bottom of the cube. Okay, so what we're left with now is p z plus dz minus pz. Really what that is the difference in pressure, which we can call the differential unit pressure dP. Okay, and that's equal to negative rho g dz. Okay, bringing our differential units on the same side of the equation, we divide by dz on both sides, and we get dP dz equals negative rho g. Okay, and that's the derivation for this basic equation of statics. Great. Give us some more room here for part 2. All right, so we've derived this first equation. It's dP dz equals negative rho g. Now that's going to be our starting point for our second question. So assuming constant density and gravity, derive an expression for the hydrostatic pressure H meters underwater. All right, so again, we're gonna start with a picture. Same container here with some fluid in it, call it water. All right, and we want to derive an expression for the hydrostatic pressure, that's P, H meters underwater. So that's maybe like down here or something like that, H, okay? Now, we derived this equation assuming that this is the positive Z direction, okay? So if we're gonna go from the surface level of the water down to H meters underwater, it's a little bit weird on the sign convention, but Z essentially is negative H, or vice versa, negative Z is positive H. We have to keep that sign convention later for when we start to integrate. It's gonna make it a lot easier for us. All right, so, and we get constant rho and constant G, that's helpful. Okay, so starting with our equation here, dP dZ equals negative rho G. Well, this is a differential equation, an ordinary differential equation, which means it's, this also happens to be separable. So we'll go ahead and separate this differential equation by multiplying our dz back to the other side. And this is going to allow us to integrate both sides with respect to the variables on them, okay? So the reason we're integrating, by the way, is because we need to effectively find the pressure at a certain depth, which means we have to take the little steps to get there, right? So if we integrate pressure, then we integrate the other side, negative rho G dz. Well, we're given in the problem that rho and G are constant, so let's go ahead and take those out. I'll rewrite this, make it a little easier. Negative rho G. All right, we have our equation that we can integrate. Now, we have to find the limits of integration here, and this is where the sign conventions and everything is important. Okay, so we need to integrate from the top down because the question's asking for H meters underwater. So starting at atmospheric pressure and then gaining pressure as we go down, also known as gauge pressure. So we're basically setting a zero pressure at the surface of the water. Obviously this isn't the case, it's atmospheric pressure at the surface of the water. But in relation to the surface of the water, we're interested in how much more pressure is H meters underwater. So for the purposes of this, we're gonna call the top of the water level, we can call it P naught, but really we're setting this equal to zero. It's gauge pressure. Okay, and then there's gonna be a pressure at depth Z, okay, or depth negative H. All right, great. So this makes this pretty easy. We're integrating from 0 to P. Now for this integral to make sense, we have to substitute a dummy variable in for pressure so that we evaluate correctly mathematically. You'll see here in a minute. Now, on the other side, we're integrating depth Z. And we said we're going from 0 to Z equals negative H. So we'll put that in our limits of integration there. Great. And now we can simply integrate. This is pretty easy. The integral of dP prime is P, and we're evaluating that from 0 to P. And that's going to be equal to negative rho G. The integral of dz is simply Z, and we're evaluating that from 0 to negative H. All right. So this equals P, and then this side comes to negative rho G times negative H, okay? Rewriting that a little bit simpler, we get P equals negative rho, rho G H. Okay, the negative signs cancel out. So this is the expression that we derived, assuming constant density and acceleration due to gravity for the hydrostatic pressure H meters underwater. It's as simple as that. All right, let's approach the last problem here, number 3. Let's get us some more space again. All right, so we got from this one, we got P equals rho G H. Great. Number 3, derive an expression for the total horizontal force on the wall of a swimming pool with a constant width W and water depth H. All right, so again, easiest to draw a picture here. Here's the wall of our swimming pool. All right, here's the base of our swimming pool, and then we got some water filled in behind it. Okay. And it gives us that the water depth is H. Okay, and maybe if we look at our wall as an elevation view, here's our water line, here's our depth H, okay, and then the width of the wall is constant. It's a square, rectangle with W. Okay, so the question states, derive an expression for the total horizontal force. Okay, so we already know that the force is going to come from the pressure of the water, and we know that pressure increases as you get deeper. So these forces are going to get bigger with some relationship, which is the relationship we've already derived, as you go deeper. Okay. Now force, this is what we're looking for in the x direction, so against the wall. All right. Well, really, I guess in this picture, I should draw these arrows like against the wall. So these are going in, right? On this one, it would be getting bigger and bigger and bigger as you go down. Okay. So we're looking for the total force in the x direction there against the wall. Now, we already discussed this, but as force relates to pressure, this, okay? So our force against the x direction completely is described by this relationship here, PA. All right, now there's a few things wrong here. Now, we have to deal with the change in pressure. The area is constant, obviously, but it's easier to write this as an integral expression. So we need to add up all the forces in the x direction from the top all the way to the bottom. And all those little forces, these differential force units, are equal to the differential pressures times the differential areas, okay? Great. All right, and then we are integrating this from the top of the water again down to H. That'll be helpful here in a minute. And we already know that pressure from our previous question is related to the depth of the water and the density of the water and the acceleration due to gravity through this expression. So let's go ahead and plug that in. Rho G H D A. Okay, so what is dA? That's the next thing we have to kind of figure out. So all these little forces act on these differential units of area, okay? But since we're integrating down this way, we want to kind of call these differential units of area like strips like this, okay? Where the width of the differential unit of area is W and the height of the differential area is DH or DZ, whatever our Z dimension is going to be called. Okay, so we can kind of write dA as W dH. Okay? Let's go ahead and rewrite that. Get rho G W H dH. All right, so what are the constants in this equation? Well, density of water is constant. The acceleration due to gravity, we're going to assume is constant throughout the depth of the water. The width of the swimming pool wall is constant. And then we're obviously integrating through H, so that's not constant. So let's go ahead and rewrite this. Rho G W, and it's going to be the integral of H dH. And we're going from, we want water depth H, so 0 to H. Again, to make this integral make sense, we have to kind of change our variables up, give it a dummy variable. I think it's probably easiest to call this Z instead of H. Okay. All right, so if we integrate this, we get rho G W, and then we get H squared over 2, and this is going to be evaluated from that 0 to Z. All right. Simplifying this, we get rho GW Z squared over 2, where Z is the depth of the water. Okay, and that's our final equation there. All right, thank you for watching, and look forward to joining you for homework 1, part B next time. Thanks.